All right, welcome to The Explainer. Today, we're going to dive into what is honestly one of the most important handoffs in the history of science. It's the story of how one absolute genius, Leonhard Euler, took the revolutionary work of another, Isaac Newton, and did something incredible. He didn't just build on it, he completely reforged it into the mathematical language that basically powers our entire modern world. You've probably heard this famous quote from Newton, and it perfectly captures how science is supposed to work, right? It's like a relay race of ideas, where one generation passes the baton to the next. But our story today is about something a little different, something more than just seeing further. Well, here's the thing. He didn't just see further. He saw the exact same world, but he saw it through a completely different lens. He saw it in a new language. And that act of translation, well, it changed everything. Okay, let's get into it. So here's our game plan. We're going to start with Newton, this absolute giant, and follow this incredible intellectual journey all the way to the powerful new physics that Euler created from his work. First, let's just set the scene a little bit. I want you to imagine it's the early 18th century. The entire world of science is living in the colossal shadow of one man, Isaac Newton. I mean, his masterpiece, the Principia Mathematica, it wasn't just a book. It was basically a new map of the entire universe. It explained why an apple falls from a tree and why the moon orbits the Earth, using the same set of laws. It was mind-blowing. But hidden inside this incredible achievement, there was this deep internal tension. And that tension, it came from the fact that Newton was, in a lot of ways, two different mathematicians rolled into one. He had these two totally distinct ways of thinking, and he really only trusted one of them. And this right here gets to the heart of Newton's private struggle. On the one hand, you had his public face, these formal geometric proofs that he felt were the only way to do real, rigorous science. But then, he had this secret weapon, a super powerful algebraic calculus he called fluxions. And this was often the tool he used to actually discover his results. He'd figure things out with his calculus, then painstakingly translate it all back into the language of geometry before he showed it to anyone. So, this is where our protagonist, a young Swiss genius named Leonhard Euler, enters the picture. He wasn't the kind of guy who would just admire Newton's finished work from afar. No, he wanted to pop the hood and see how the engine actually worked. You know, Euler said it perfectly himself. Reading Newton's Principia was like looking at a beautiful finished sculpture. You could see the final form, sure, but you had absolutely no idea how the sculptor actually carved it. Euler realized that these geometric proofs were a destination, not a roadmap. So if he was going to make any real progress, he had to reverse engineer the Principia. He had to translate Newton's physics back into that powerful, flexible language of analysis, the language of algebra, of functions, of calculus. Okay, so what did this translation actually let him do? I mean, what's the big deal? Let's look at a fantastic, really concrete example of how this new language just blew the doors open to a whole new world of physics. So Newton's laws were amazing for describing the motion of planets and stars. And why is that? Well, because from way down here on Earth, a huge planet like Jupiter is, for all practical purposes, just a single point of mass moving through space. The laws work perfectly for that. And here's the rub. How do you use a law that's designed for a single point to describe the beautiful, chaotic motion of a spinning top, where every single particle is flying off in a different direction? Newton's original framework, it just didn't really have a good answer for that. And this is it's pure genius. This is Euler's breakthrough. By translating physics into the language of analysis, he could generalize Newton's work. His new laws of motion didn't just tell you where an object's center of mass was going. No, they could also describe how the object itself was rotating around that center. By introducing these powerful new ideas like torque and angular momentum, he literally gave physics the vocabulary to talk about spinning. But you know what? This new approach didn't just solve new problems in physics. It actually created a deep and, honestly, a lasting split in the entire mathematical world. You could call it a great divergence between two completely different ways of thinking. You can see the fork in the road right here on this timeline. While Euler is just charging ahead with his analytical mechanics, a lot of British mathematicians, like Colin Maclaurin, they were digging in their heels. They were trying to defend Newton's original geometric style. So while Euler was making analysis more powerful, they were trying to make geometry more rigorous.
And here's the really crucial point. The two schools started asking fundamentally different questions. For the British school, math was still tied to pictures, to geometry. It was about describing physical curves in space. But Euler's school, they took this massive leap into abstraction. For them, the real object of study wasn't the curve you could draw, but the function, that symbolic algebraic expression that described the curve. That was the real star of the show. By freeing mathematics from always having to refer back to a picture, Euler and his colleagues created what we can call Eulerian calculus. And this just unleashed a flood of powerful new tools. Things like partial differential equations, which let us describe everything from heat flow to the waves in an ocean, or the calculus of variations, which helps us find the most efficient path for something to travel. This became the language of physics for the next 200 years.
Okay, so this brings us to the real heart of the story. Euler's relationship to Newton wasn't just simple succession, one guy after the other. It was a profound transformation. So let's put it all together. Euler didn't just add a few chapters to Newton's book. He saw the genius that was hidden inside Newton's private analytical methods, and he did what Newton himself just wouldn't do. He rewrote the entire story of physics in that powerful algebraic language. It was a translation that unlocked physics for generations to come, and it paved the way for other giants like Lagrange and Laplace.
It's such a powerful idea when you think about it, that sometimes the biggest leap forward isn't finding a new answer, but finding a completely new language that lets you ask better questions. And that really makes you wonder, doesn't it? What other scientific revolutions out there were not just discoveries, but were really translations into a more powerful language?